share screen a little bit later?
No, you could start sharing whenever you'd like.
Okay.
Yeah, you can't see the screen you're projected on here, but it's on the side of on the other side of the room.
That's no problem. You might be able to give me some information on the audience. Is this one of the graduate student class or?
Yeah, so most of the people in the room today are graduate students, and there will be a mix of faculty as well.
All right.
Okay, I guess that's good then. Keep watching.
Oh, fantastic.
Also, I told her we'll do a intro and a small announcement.
Cool. Cool. One of your students, he was in my class lesson too. Yeah, he was heading over to the other room, the last semester, to that car.
We're doing last one.
Okay, gotcha. Yeah, I need to organize one of those. Oh, that's kind of a little messy. Time to go.
There were a bunch of things that were NPY labeled.
Oh, really?
Yeah, well, because we were just that stuff, like, not old. But
Oh, okay.
like just being in use, like, who is NPY?
Oh. That's a good point. So yeah, Haley should be putting her, if it's Haley, I don't know, she should be putting her name on it then.
He didn't know who that was either. So,
Okay.
like, that's like, it was just like a little
Yeah.
NPY, like HR on it.
Oh, okay, so she at least put the.
Yeah.
Okay,
I was like, who's NPY? Like HR is the initial one. Everyone here should be able to record their Moodle attendance. That should be open. I'll give it a couple minutes and then we go over that.
Did you do anything fun over the break?
Yeah, not
Lots of nothing. Hopefully sleep at least between the nothing.
What about you guys? Did you have family travel?
Yeah, we did a bit of travel. We drove up to DC and then saw my family there, and then flew to Boston from there. Saw Steph's family there, and came back down. I felt like it was just a lot of running after little kids.
I went up to Richmond, but I did nothing. We did nothing.
Okay.
And then we both came back down.
Got it, yeah. You didn't get affected by the whole snowstorm thing, right? Okay, yeah. Yeah, we were gonna leave actually that day, and then we saw it coming down. We woke up, we're like, yep, we're not gonna try this.
Yeah.
It reminded me a lot of Atlanta a few years ago. And the snow apocalypse, I think was the nickname they gave
Were
it.
you in Atlanta? It was maybe 2010, 11.
Yeah,
Yeah.
exactly.
I was flying back through Atlanta. I drive from Atlanta to Clemson.
Okay, yeah. Oh, wow. So were you stuck? I mean,
My advisor drove and it was like 2 miles an hour. He had like that SUV that was parked at the airport. And it was 2 miles an hour. Like just trucking along.
yes, some progress is better than no progress.
Yeah. Like it was after, like we weren't in the storm, but we flew back right after.
Okay.
Recording has begun.
All right, everyone. It's time to get started with our first seminar of the semester. Welcome back for those of you who were last semester for your faces. Food and drink has arrived, so please quietly grab some as we get started. Quick reminder to everyone about attendance. The attendance login on Moodle opens up a little bit before class and it runs till about 10:30. I think I have it set up, so you should be able to enter your attendance. Please log your attendance. If it's after that time, it's considered late and not attending. Hopefully enjoy all the seminars, enjoy all the food. Today we have an interesting seminar. I think actually different topic than we've had in last semester, and it's Dr. Liu and coming from University of Tennessee at Knoxville, the Oak Ridge National Lab. So for some of you who don't know, there's a connection there, a national lab and a university. And the talk we're going to have today is about the benefit of grid edge synchronized measurements. So sort of edge computing, grid power optimization. And I think that hits home with a lot of the students here today. So without further ado, I'll turn it over to Dr. Liu. The class runs till about 11:30, but if you want to end a little bit earlier, we'll have some time for questions. Thanks for joining us.
Very good. Thanks a lot. Can you hear me okay?
I think so. Everyone in the class? Yep, we're great.
Good, good. And you can see the screen all right?
Yes.
Okay, very good then. Okay, I'll get started. So basically, I'll try to give an update on our monitoring system and the applications are being developed at the University of Tennessee and the Oak Ridge National Lab. So many of your faculty are actually familiar with the monitoring system. And however, I would think maybe some of our students are actually new to this system. So let me see if I can find a way to advance the slides. Okay, great, very good. So what we have developed starting from Virginia Tech time and continued after I moved over to University of Tennessee and the Oak Ridge National Lab as a joint appointment. And we took the system, which is the phasor measurement, but in this case is a single phase. And this was invented at Virginia Tech, but we further and deployed the system. The main purpose of having a deployment by the university is our student would have data because many of the measurements are kept, private and proprietary information at the substation level by different entities. Having a real system that's streaming data to our site, which is UT and Oak Ridge National Lab, is extremely beneficial for our research as well as the learning process for students. Both graduate and undergraduate student has enjoyed play with the data and looking at different aspects that we were able to see. I wanted to also mention that we do have deployment at NC State. I don't know how many in the Raleigh general area, but one of our site is on your campus, okay? So what are those? Those are actually phasor measurement. Basically, if you heard about PMUs, those are PMUs. So it's a synchronized time measurement. However, when you get the voltage waveform at a very low voltage, in this case, we deploy them in offices, student dorms, residential areas, and schools, hospitals. We were talking about McDonald's, police stations, and so on. So you take measurement 110 and you actually calculate the phasor, which in this case is the voltage magnitude in RMS, as well as the angle. Now, this angle is actually not the angle between voltage and current, which most of you very familiar, that's important property. But this is the angle between two substations, you know, or in other words, this is the angle when your voltage waveform cross zero, and that's against absolute time. So once we have a GPS timestamp for all the data, we can compare information easily and be able to have a whole picture of the grid. Okay, let me move to the second page, which covers, which talks about where it's covered worldwide. So we do collect data. I'm thinking, looking at Greenland, we probably will get to there at some point. But we do take data from all the major grid worldwide, and this is also for us to understand the different properties of the grid, and also for us to understand some of the countries like Ireland and others, and also part of our Hawaii system, Hawaii island system, have a much higher renewable penetration, and we can actually know ahead of time before US becomes, before the main grid becomes high renewable, what are the issues, what are the phenomena, and so you get to peek into the future. So that's part of the reason for the worldwide deployment of the units. Let me start by going through, this is a movie we created by giving our students, researchers, feel about what are we expected to see in the power grid. So here we have one monitor that's reported a first trip in Florida. And because of that generation trip, this is a few 100 megawatt, it sets a major wave across the US. And this is very typical. It happens every other day almost. And this is the phenomena that actually we can capture and we can show easily with time synchronized measurement. Now here you can see on the left, it's actually the frequency at different points. And this is an earlier graph. That's why you see less dots. Yeah, but it's quite interesting in the sense that we are able to combine with some of the industry measurement points and then formulate a replay of a system. And here is what we're actually seeing in terms of why do you see a wave moving? Because the electromechanical propagation of events actually took time, and they're traveling like 500 miles per second, much smaller, much slower than the speed of light. So our measurement technology and the accuracy of the GPS timing could capture that delay. And here, and this particular delay allow you to calculate back where the source is and how big is the event. So here is our typical report of that goes to industry, NERC, DOE, FERC, and some private entities who are members of the consortium, that they will get, this is a different event. This happened, in the middle of the country, now the Florida one. So this is a typical report that we were able to generate because of the monitoring system and because the time delay of the traveling wave, electromechanical wave, and because of the data were collected throughout the system. So basically, this is a monitoring system that cross utility boundaries. Now, some of you familiar with the U.S. Power supply structure. So it's usually owned by private entities, except the major hydro units, and they are able to see their own system, but they are not typically be able to see what's happening in their neighbors. If you look at the graph on the right, you understand that the country was served by and connected in 3 major areas. So when you're connected to your neighbors, however, you don't know what your neighbor is doing, and that's a little frightening. And this allow, to some extent, people to know what's going on outside their system. So it becomes a situational awareness tool besides, other uses for this. Let me go over another one of our recording, and this is when the storm actually passed through TVA area. That causes a lot of transmission. 500 kV system, actually the tower collapsed. So I think 11 or 12 of those, which is a major part in TVA, actually were hit real hard by the storm and caused the major oscillations as well as collapse of the mechanical structure. So you can reflect many things from the measurement. And lately, we have been focusing on a lot on how to deal with major oscillations. So how do you actually use the measurement data and be able to damp out oscillations? So here, if you can see that there's a growing oscillation that can be observed in those kind of oscillation has observed in the West, as well as in the large European system. There is some threat in terms of blocking the real power flowing, taking up space for real power to flow in the transmission line if you have this oscillation going back and forth, to the extent that you may have those oscillations so big that you actually could cause system stability problems, and you peel, or another way to look at it is some of the system couldn't keep up with the oscillation, you actually cause the system to island. Yeah. So there has been quite an effort to damp system oscillation damping in our team, and this involves helping Italy. And this is actually an effort where you observe the major oscillation mode as shown in the left picture there. And then before it grows real bad, you do have time to actually suppress it based on intelligent measurement and control. This is actually oscillation that happened between Italy and the rest of the Europe. Now you notice there's some phenomena that's very similar to Florida because it's an island, not as a peninsula, I should say, and it has a very relatively weaker connection to the main grid. So that's what happens when you have a major disturbance. You tend to have oscillations. Yeah. So we have been making use of the data in terms of situation awareness, but in this case is taking action. So for this Italian system, we have got into phase 3, which when you study a system, you first doing some simulation, and then you likely run some real-time simulation like RTDS, OpenRT, or Typhoon type of analysis, right? And then we actually are into the third phase, trying to test our system in the field to get it actually implemented in the system. We have also similar concerns in the US. as the renewable increase, you actually have much more likelihood of oscillations because your system inertia actually reduces. And you also have other things that are a little bit beyond, well, let's put it this way. So if you have system that's low inertia and a lot of IBRs or inverter-based resources, like an interface between solar and the grid, interface between wind in some cases, and the system, and interface between your storage and the system. Those are power electronics, which NC State has a very strong program, right? Those power electronics are less understood, and they are more they are a lot faster than the synchronous machine. When I say less understood, is comparing with a conventional machine that moves reasonably. Dynamics moves slow, not rotating slow, but the machine has large inertia. It doesn't change its state real quick. But power electronics can actually change extremely fast. It's a great capability, but it's a curse, if you are dealing with a fast thing in the system and a bunch of slow things, you are going to have issues. That's just one side of it. And also there are many interactions between power electronics devices that we are less familiar with. So you have a lot of potential to have oscillations. And this is the one we're looking into for New York Power Authority, where they have an issue between East and West. So this is also making use of the monitoring system and be able to suppress oscillations quickly. And we have another ongoing work with Saudi. They also have an issue, and this is not oscillation, not just an oscillation issue, but it's a stability issue. That's caused by oscillation because of the oscillation, their out of step relay kicks in, and that separate the grid, which is the separation is between the source and the load, which actually cause blackout to some regions. Yeah, so that's another application using time synchronized or phasor monitoring to deal with this. Okay, we have just started the program with UK to actually use HVDC. So you ask, how do you damp them? Well, you can use governor, you can use fax device. In the case of the connection between Scotland and England, they have a lot of HVDC, so you can use HVDC to actually modulate it to damp oscillations. So that's another issue. So has been a growing concern in terms of oscillations, and I haven't mentioned that we work with some of our Hawaii Island, and they also see tremendous size oscillations that are need to be taken care of. Okay, now the oscillations I mentioned earlier are actually natural frequency oscillations. They are caused typically after a band, one disturbance, but some of them are actually long lasting. The ones I mentioned earlier usually they last, in terms of for example, 5 seconds, 10 seconds, 20 seconds. But this one I'm showing you another problem starting from Florida is actually oscillation that lasted 20 minutes. So it's smaller magnitude. If you look at the scale on the left, you can see that the frequency only changed a fraction of a second, right? But this is long lasting, and it is actually possible to cause mechanical failures and other things in the system. You don't want this either, and you need to have ways to suppress this as well. So there's a lot of work that need to be considered in terms of, when we have a grid that's easy to move, then we have to have ways to watch for those growing movement that's undesirable, in this case, oscillations at many different frequencies, okay? So give people some rough idea. This is looking at 2013 and 2015. This is way before a lot of renewables are online. And even now we have only small fraction of renewables in most part of country, except, some part of West California, where you could go high. But what we're seeing is you do have large amount of oscillations. This is 12,000 is what we see that are, reasonably significant size within 2 years in the Eastern interconnection, which is where we all are, yeah. And they tend to go very high in certain hours and low in other times. And that is because the inertia actually change in the 24-hour period. Okay. Now notice this is the UTC time. So we needed to convert that into our local time in order to get a sense of when the low times are. Usually in the East, usually they're in the at night. However, in Hawaii system, solar is very high during the day, so the low inertia times are actually during the daytime. So this curve would be reversed, and that's what people would call a duck curve. But right now, what you're seeing is a very typical large system load profile or inertia profile. Okay, but this could totally reverse and change into a very hard to manage system with very small inertia. Okay, so there is a need to know, we've showed a lot of oscillation. There's a need to know where and who and what is causing the oscillation, right? If you find out where, usually a generation station has multiple machines, you would like to know which one. Even you know which one, you may not be able to interfere easily, because if you find out that's a nuclear, you're not going to shut it down. And you wanted to know, okay, is it my electrical system, excitation system, or mechanical system that's causing it? And I may need to make adjustment. I'm not going to shut a nuclear plant down easily, because that's not what you that's not something you actually designed to do, right? Yeah. So locating the source of forced oscillation, or even just the regular oscillation, is important. And that's very interesting research work being carried out by all different groups and using different approach. But none of the group can do anything without this time synchronized measurement. It can be Phasor, like here we said the angle and the magnitude, or it can be just a waveform record, right? Either one is possible. The reason people use Phasor is because our power grid, our large grid, actually were mathematically easily computed or controlled in terms of Phasor. Now, when you have IBRs, you have a lot of fast phenomena, the Phasor would be too slow. and you may need the point of wave or just taking the waveform directly. So here are some older information on the islanding phenomena we detected. And this is a large system island. Like I said, a large piece of the grid becomes independent. And this could be okay. This could be very dangerous because you don't necessarily balance the load in the system. And then you have to end up losing load or have to shut down generation. And that's not desirable. People try every effort to avoid it. But this can be actually detected and without too much difficulty. And this also tied to microgrid. Basically, microgrid, you basically are a system where you prepare to be islanded. Most systems don't prepare to be islanded. So microgrid control would benefit from, this time synchronized measurement as well. Here is an example of somewhat island system, same phenomena. You have a different frequency signature, you can detect that. But this is a different case where you have UPS backup, you don't have an issue, you're load only, right? Let's see a data center, a hospital, at least most of the time you're load, and then your backup kick in. But remember, all the backup are time limited and of course costly. So you do like to know how much time the backup can last and so on. And this is something we try to develop and implement for DOE is to have a knowledge of all the major hospitals in the US. If there's a major disaster, how many regional hospitals are without power for how long. And you can easily observe this without having to tap in from the system into the circuit. You can just monitor that from frequency, also, relatively easily without connecting to the guts of the system. Yeah. Okay, line trip detection and as well as capacitor switching, you can easily see those from even for the 10 points per second measurement. What I mean measurement is the output, not necessarily the sampling, which is a lot faster. Okay. All right. Let me move into a different topic. Remember, I mentioned quite a bit on system inertia, right? We kind of know the system inertia fairly easily because we know how many generators are online. And we also know, what percentage of load contribute in terms of inertia, those coming from induction machines. They're not as strong as synchronous generators in terms of inertia contribution, but they do provide some inertia because they're not tightly coupled as a synchronous machine, but they still have some mechanical contribution loosely coupled between rotor and the stator because it's not synchronized. It runs on a slit for the induction machine. However, if the grid start to change quite a bit between different time of the day, let's see, at noon I am mostly supplied by solar. In the evening hours or morning hours, I really have to crack up my other generations. So also my solar, my wind may also be contributing to inertia if it's running in a grid forming, or my storage contributing to inertia in a grid forming mode. and that could change the total inertia. So there is a need in general to know what is the system inertia at a certain point. And what you're looking at is actually a study that's forecasting inertia in the 3 US interconnections. Here I only listed 2 because those 2 are the problematic ones. When we get to instantaneously 80% renewable. Yeah, you see the ERCOT already got into that part because they were able to get to quite high momentarily and during the peak solar time and wind generation. And if we get to 80% instantaneous, we notice that even the Western interconnection, which is reasonably large, not as big as Eastern, also could run into low inertia problems. The line indicate you drop load at a different time delay, right? So, so being able to understand and quickly monitor inertia is one of the things that the phasor measurement can do, and you don't need to be at the high voltage side. You can just do it from measurement at the distribution level, okay? So how do you do that? You actually use the slope or ROCF, rate of change of frequency, because your slope or your ROCF is proportional to 2 things. One is the system inertia, and one is how much generation is lost. And this is a generator trip case. So if you know how many megawatt is lost, and you know the ROCF from measurement, and you can calculate system inertia. So as you know, there's many other secondary process that affect this number. However, this is the major dominant factor determining ROCF in a grid. So it's not impossible. It's quite easy if you constantly have large disturbances like this. But you don't want a system to have this kind of disturbance, and so you don't constantly get drops like this. So there are other ways to find inertia, and you can do it with ambient data. If you recall, at different time of the day, the number of oscillations happen differently. And that's a way to say that any minor change in the system, load change, other change, topology change, could cause some kind of disturbance, and you excite the system. And based on that, you can use ambient data to estimate inertia in the grid. And this is some results from estimation for the WAC system. It's compared to the ground truth because NERC collect that information for the system as well. Okay, and you could probably guess what we're looking at here. This is actually inertia estimate from ambient frequency signal for a small island system. Yeah, you can see, you could have variations during the non-solar time, but during the day in the middle, you can see when the solar is doing well, you have almost zero inertia. And I think that also shows the estimation using, ambient data is quite interesting. Remember, if some of you work in dynamics, you know there's a dead band. And so it's not that straightforward. There's a dead band involved. So it's some nonlinear behavior in the system. So it's so you can, so that makes the problem interesting, challenging, right? Yeah. Okay, so let me switch gear to a few other things that can be done. I think we're 10:50. Okay, so we're doing okay time-wise. Oh, I want to make sure you have enough time to do questions. Yeah. So here we're looking at Eastern interconnection model validation. If you look at the left graph, that showing the big gap where the arrow is showing between measurement and the model results. So once you are able to get the measurement, and then you have a way to make adjustment to the model so that your model can reasonably match your measurement, which is between the green and the blue line. Yeah. And on the right, basically, you see many other locations of this event used to do model validation. Now, remember, when you do model validation, you only somehow tweak the model to that instant of the measurement, because the system dispatch change, load change, and every moment is somewhat different, right? Even for the same season. So that need to be kept in mind. We can also use phasor measurement to look at the system model in the much simplistic way, at least for now, because you can look at the power grid as a, just look at, assuming that's a linear system. This is true most of the time, even you have 2 gigawatt generation trip that causes a large local disturbance, but for the whole system, it's still linear. So you can actually take the measurement as if you are exciting a system and you get a response somewhere else as the output. So you can calculate transfer function of the power grid, and that makes it very simple to deal with a lot of issues in the system. And that's part of the principle our oscillation damping control was based on. And that opened up very large area of possibilities. You can do, equivalencing of a system based on measurement. You don't have to run. Let's say you wanted to, TVA wanted to run transient analysis faster than real time, right? You cannot do that running the whole EI. You're far from doing that. However, if you can have a very accurate equivalencing of the grid at that moment, you can actually have a very good and small accurate model of the TVA system only. And then you do have a capability to carry out analysis of in a faster than real time. And why do we need a faster real time? Because you wanted to be able to predict before a catastrophe happens, right? You want to look ahead, and that's one of the things that measurement monitoring can contribute, because you simplify your problem that makes computation much more efficient. Right? Another interesting thing, this is nothing to do with power grid operation, but everything to do with power system as well. So this is a more like a forensic analysis. We have, if we look at our frequency, if we also look at the digital recordings of a speech, right? Or a video recording of a movie, let's see YouTube. And people do use YouTube to identify where the YouTube movie was recorded. Yeah. So you can actually pinpoint, because the 60 hertz frequency get embedded in many of our digital signals, either by electromagnetic coupling, or by mechanical coupling, or by optical coupling. Somehow they get in there. So if you do a signal processing, you can extract the power frequency out of that information. So if you look at the signal, if you look at the recording one of our postdoc did for her speech on the left bottom figure, that's her voice recording. And we can see, okay, there's the 60 hertz signal, there's the 120 hertz signal, and you have some aliasing other signals in there as well. So if you take out the 60 or 120 hertz signal and you do analysis, you can actually match the frequency at that time. On the right, you also see, so the top one was the Houston Police Department recording versus our FDR data. And you can see the matching between their voice recording and our frequency monitor recording in terms of frequency signature. You know, you may be able to have other signatures, but this is the since we focus on, the frequency of the grid. Yeah. So this become a DNA in the sense that you can actually use your frequency signal. If you keep all your historical signal and at certain locations, you can use that to identify the time of the recording, and for a large part, not very, not able to tell from building to building because we don't have that very detailed base. But we can actually pinpoint the location to some extent, at least, major regions, as well as the time, 2 seconds. So if someone wanted to, doctor a recording, either cut or insert anything there, and you can use our frequency database to authenticate and be able to tell that. And we were talking about, many controversial recordings, including Nixon or where bin Laden was located. Those can all be done, actually, if we have a ground truth measurement. Even you don't have ground truth measurement, you can capture the cutoff. You see a frequency going a certain way, and suddenly there is a jump that's too fast for a grid. Then you can also detect any, doctoring process in a recording. So this becomes very interesting database for authentication purpose as well. Okay, let me go reasonably faster. That way you guys have more chance to look at the, to have questions. So we do a lot of work related to the hardware itself, because we build our own software, we build our own device. Of course, the hardware itself was farmed out to do outside. And we used to do our soldering for the first few units, but we continuously change, modify, and improve units as well. Yeah. So one thing I wanted to point out, the GPS time signal is not reliable, and it's weather affected, and it is subject to spoofing. And here is showing that between commercial PMUs and our units, very similar phenomena is during the period we were observing 2010, 2012, at least half of them had suffered GPS problems. So this is something has to be dealt with. And of course, you can use atomic clock. Here's some way to use the backup atomic clock to ride through some period where the GPS has problems, and you can have some other ways. And we also look at the E-Lorraine and some other ground-based systems. Yeah, and right now we're looking at Phasor, which is something you cannot destroy, and but it's not inexpensive to use. You have to have huge antennas to do that. Okay, measurement. So measurement done by connecting to a wall in an office is reasonably easy, but that prevents you from having a direct angle measurement, because transformers in between you and the substation is going to have some other arbitrary shift, right? And so you can use magnetic field and electric field. So we've been developing those for contactless measurement. We're trying to reduce the cost so we can have one, you can almost have one unit in each household. It's a tall order and may not be necessary, but reduce the cost will also make it easy for putting those in all the rooftop solars and other devices that are all over the place. So a cell phone based device might work. There has been a lot of requests for people to design a system that measures power quality as well as phasor and point of wave. So you can put those all three in one unit. And we do have units that can do that. But most of our measurement are most focused on simply the single phase voltage based phasor. The last item I like to talk about is the deployment. And there has been quite different effort to deploy in many regions of the world, and this is the US region in Puerto Rico. After the hurricane, the Department of Energy wanted to, increase the situation awareness, and we are deploying systems there. And there's also different part of the world that got interested, especially in university, because they can afford, that are interested in deploying their own systems for research purposes. So quite a bit work are ongoing, and it's getting more and more challenging because the system's inertia reduce, and also the complexity of the system increase because of the renewable integration. So there's a tremendous work that need to be done, and for students who are interested in this area, there's all kinds of interesting work. In our case, we have a team of usually happening between 20 to 30 students. Some work on the IT area. So the server, the data, you're pretty much have to guarantee the data coming in 24/7. Not the end of the world, but you're gonna get all kinds of alerts and people calling if it stops for a little bit. Yeah, actually. We have a large team dealing with the hardware, and they like to invent new circuit, new devices. And we have another large team that are actually working on data processing, machine learning, and then another team work on large system simulations. The reason is what you observe in the system tied to phenomena that you like to duplicate or the other way around. So that's why we're also interested in large system modeling and simulation. So if any of our people wanted to dig further, I will share the slides with the NC State team, and you can dig into this some of the links of our work. So at this point, let me stop end the talk and be happy to answer any questions that that you may have.
Sorry, I was muted on the Zoom side. Thank you.
Thank you.
Questions from the students?
All right.
Yeah, Devin.
This database, is this public?
Can you, I don't know if you could hear that. He asked if the database is public.
Yes, the database, we do have a public website. The database itself, all the data were not made public. The reason being that many of our hosts are utilities, and they would like to have the data coming in be private. However, there are two things that are I like to mention. We do have a public website, which is at the very end of the, yeah, here. You can see that the public, yeah. The first website shows fnetpublic.utk.edu. That one is a public website. You can observe all the measured information from all over the world. However, no one, you know, however, whenever people need some data, and they always need it for a small fraction of the time. So we actually do share some of the events that usually satisfy the need for research purposes. Yeah. Okay, good question.
So there's a couple questions I'll read that came in through the chat. The first one is, how do high voltage DC links come into play with these synchronized measurements, since there is no angle information in DC systems?
Okay. Interesting question. At this moment, the measurement was done on the AC side. So if you look at the DC link, right? Usually there's an inverter, there's a converter somewhere else, and that's your DC segment, right? So the measurement was actually done on the AC side, where you do have a way to know the angle as well, and there will be an angle. If you pretend the DC is a little black box, then between A and B there will be an angle. You can treat it as if the DC doesn't exist, and you do have a power flow between A and B on the AC based on AC system. Yeah.
Thank you. The second question from Professor Liu here at NC State is, as FNET sensors are deployed in distribution grids and their measurements are one-phase measurements, I wonder how you will compare data collected from the different phases to extract angle information in a consistent way.
That's a good question. Yeah. The way you assume, that's quite interesting. Yeah. So yes, we could be connected to quite a different phases, but there are only 3 of them. So you know the angle between them, so you can line them up that way. Yeah, good question. And another point I want to make is, because we're measuring a distribution system, not only we don't know which phase ABC we're on, we also don't know what's the phase change between the high voltage substation, which is what we really like to know, and my house, right? So I don't know that. So that is an unknown factor. However, one thing do remember is I don't have to know that in order to know. See, whenever something change in the system, right, I'm interested. So any delta change in the angle is observable regardless of the reference. Even I don't know the reference in terms of what's the, the reference is relatively stationary compared with the sudden angle change, so the increment change of angle is what I'm interested in. I can somewhat ignore the angle, the stationary angle difference, the relatively stationary angle difference between my data and monitoring data points.
Excellent. So one more question came in through the chat from Professor Wong here at NC State. He says, thank you for the informative presentation. He does research on ENF extraction from multimedia content, such as videos and rolling shutter capture
Really great.
images.
Yeah.
He wants to know, in your view, what will be the opportunities for signal processing, machine learning folks in kind of this field, this area, and what's the next step for them maybe?
Yeah, I think one thing we definitely need, well, there's not just one thing, many things. You needed for a reasonably longer period of time to extract information, and also each, also the pattern for each monitoring site is different. I'm thinking, in terms of AI application, most likely there is a way to study the noise pattern in a specific site and then use that noise pattern to extract data as a way instead of just the non-AI approach, because the noise pattern also has the noise pattern in certain location is a little bit complicated and it's time varying as well. So that's one way to think about things. Also, if you have multiple data points, and you can also use one as a reference to extract. So there can be quite a few complicated challenges involved in this area. Yeah, the overall difficulty is the signal to noise ratio coming from the different media, but correlation between different location and the longer time period, maybe some more intelligent algorithms, use machine learning could be add some value to this. I actually looking forward to have a discussion. Yeah, I think we are going to talk later on.
Awesome. Yep. Professor Wong says, thanks. Any questions from the audience? More questions, I should say. All right. If not, let's thank our speaker for kicking us off this semester. And for those of you who have meetings with Dr. Liu, please be sure to log on later today. Thanks again.
Thank you. Thanks for the opportunity. Yeah,
Thank you.
I will be sending the PDF PowerPoint. It's huge. It's like 60 megabyte. So I'll send the PDF version later on in case
We'll link it up with the videos.
Okay, very good. That's good then. Thank
so
you.
much. All right.
Okay, bye. Have a good day. Yeah.